Welcome back. So in previous lecture we discussed mostly about the change in the channel pattern because of tectonic deformation, and after completing this topic on tectonic geomorphology, I would like to discuss two more examples from Kutch, Great Run of Kutch and Himalayas, where we have identified evidence of change in channel pattern as well as the direction, or I would say the diversion of the channel, the main channel of major river system took place during geological past because of active tectonic deformation. And this is basically important because, and I hope it will interest you people, because this change of the channel or diversion of the channel affected the habitation, one of the major settlements in Gujarat, and that was Dholavira, which was like 4,500 years back. It so happened. So and even in Himalaya it affected, and in the future it will keep on happening. So this is important topic for all of us to understand that what generally happens when there is an influence of active deformation. So under the purview of the tectonic geomorphology, we were going to discuss this topic and the evidence of tectonic geomorphology from Himalayas and from Kutch. So before we go ahead with that topic, let us finish few things which are also important and related to the basically the change in the channel pattern. So we had a few slides on which we discussed about the river from New Madrid, which was influenced because of the county uplift. So before the uplift, where the river crosses the uplift, and so before in the upstream and the downstream, and while crossing the uplifted area, how the drainage pattern changed, that what we discussed in the previous lecture. So let's start with this. So if you look at this slide, this shows that this is of the Mississippi River in the New Madrid Ridge, and the uplift. So above the uplift axis, what it shows that is the city name is Cairo, and Hickman, the river channel is relatively straight. That what you can see here, it is quite straight channel, and this is before the axis of the uplift. So this is the axis, it comes here and before that, and then however the downstream of from Hickman town, the river has high sinuosity pattern. So it becomes highly sinus as it moves downstream from the Hickman side. So this is one of the important point which you should note it down, that the change in the elevation, or you can say the relative gradient of within the channel pattern, let's say within the channel or the river bed, the channel pattern will change or it will be affected. So this is very important. Now this is again the same area which shows the sinuosity pattern in different portions, and this is what they have done, that reach 1, reach 2 and reach 3 they have tried to look at in detail in smaller segments the change in the channel pattern or the sinuosity, whether it is highly sinus or less sinus, or the channel has become straight. So this is the zone of uplift which shows the less sinuosity. So what it shows is that the classical example occurs where the Mississippi River crosses the Lake County, a 10-meter high topographic bulge caused by active deformation in New Madrid region. So New Madrid region, as I was talking about, is the part of the stable continent. It's been considered as a stable continent, but this area is seismically active region, and this is well been like justified by the occurrence of small and large magnitude earthquakes in this region and continuous monitoring of the seismic activity in this. So here what it says that the low gradient, the Mississippi River, the gradient is almost like very low, 0.0001. Mississippi River reduces its sinuosity on the up dip flank of the uplift where the gradient are lowered. So gradients basically is on the uplift part where you are having the bulge or the warp. So on the upstream side the gradient is lower because of the uplift. On the down dip flank where the gradients are increased, the sinuosity increases. So this you have to keep in mind, and one of the previous slide we also gave with the cartoon that if you lower the gradient, then the sinuosity reduces, and if you increase the gradient, the sinuosity increases. So this point is extremely important. And as I was mentioning in one of the lecture, that whole Indian plate is under deformation. So if you are having a local change in the channel pattern, which also we learn in during this topic of tectonic geomorphology, that local ponding, local braided channels, or the local evidence of local meandering and all that could be considered as the signatures of active deformation. Nevertheless, this could also happen because of excess amount of bed load which has been supplied to the main channel by the tributary. So one has to be careful, but in total what we can justify this part is that the change in the gradient in any region or any portion of the channel or river valley will result into change in the channel pattern. So this is a direct evidence or the signature which will indicate you the ongoing deformation. So in the Indo-Gangetic plain, one can also look for such signatures and identify the pockets where the ongoing deformation, the tectonic deformation between the Indian plate and the Eurasian plate is influencing, and the overall plate and the local deformation is taking place, and that can also result into the diversion of the channels and all that. So that we will look in the coming lecture. So let's move further and see. So this is the area of zone of uplift which has been marked by the red portion. So investigation along Soan Dune, this is what I was showing, but now I would like to discuss this in little bit greater detail. So in the previous lecture I was showing about the portion from here, this area, that is a warping which we identified, and where we talked about the drainage pattern. So we were able to pick up the radial drainage pattern which has been shown here, but in this topic I am going to talk about this portion here, where the drainage channel pattern has changed because of the change in the gradient here. So as I told earlier also, that this area is been occupied by the lower Shivalik hills, as well as the younger deposits, quaternary deposits, which has been shown here. So these are all the tertiary hills, but some portion on the top of this is been covered by the younger deposits, which have been shown here as Q0. So this is a geomorphic map of the area, and this symbols, they mark the fault lines over here, and this portion, as I have shown here by double arrow, is the active folding. So active folding is taking place along with there is a fault here which has not been marked, but there is a fault here, and then in some locations what we see is this active flexure. Active flexure has been shown here, and this symbol is active fault, and these are all thrust fault, but the symbol which has been shown with the comb on this direction, this side, means that this portion of the surface is down and this portion is up. So this is a thrust fault within fault dipping in an almost northeast direction. So this is another one, and then this one is the direction of tilting. So this portion has been tilted in the same direction, that is in the northeast direction. So this is a warp, or we can say the folding flexure which has developed here, and so on. So we have the fault line which runs through this one here, which we later on we identified, and the deformation of the landform is well reflected by drainage pattern here, as well as change in the channel pattern over here. So drainage pattern which shows radial drainage, and we have already seen the warp here. So this is the succession in the exposed road side, as well as in the river valley, which shows the tertiary deposits, and high resolution satellite photograph which shows the drainage pattern, almost radial drainage pattern and circular, which you see here. So this portion is higher ground. This we have already discussed, so I'll just move ahead. And the most important one which I would like to discuss here is this area here, this one. So if the arrows which I have marked here shows the trace of the fault, and this side is up of the fault, this side is down, and it also, in the previous slide which I was showing, it also shows the tilting in this direction. So it is back tilted because of the deformation along the thrust fault here. So let's see this close up of this one. So carefully if you look at, then you find that the channel is quite tight here in the sense of the sinuosity. So tight meandering or tight sinus channel, all channels which are crossing this line, this is fault line here, shows the tight meandering. So next slide, if you look at this one here, this is more close up of that, so you can easily make out that as soon as it crosses the thrust folded area here, this is a fold here. So as soon as it crosses this line, of course the straightness of this feature is also because of the local people or the administration has constructed the road here, because they found the topography, the best topography to have the flat area adjacent to the slightly elevated portion. So they have also used this advantage as to construct the road. So this has the road runs parallel to the fault line, and this is a deformational feature. So as soon as it crosses this line here, the sinuosity reduces, the channel become almost straight. So you can see here also the channel become almost straight. So local deformation in any region, tectonically active region, will result into the change in the channel pattern. So you have a tight meander. Just a similar example we saw from the Jwalamukhi thrust from the higher Himalayas. Not from the higher Himalayas, but it is all the portion of the lesser Himalayas, and this we talked in the previous lecture. So similar example, very similar, that the Bias river which was crossing the Jwalamukhi thrust shows tight meandering before it crosses the fault line, and then it becomes straight. And similarly here also there is the thrust fault and fold, related fold, which has affected the channel pattern. So please remember that you have the higher sinusity, and as soon as it crosses this portion, then it becomes the sinusity reduces. Now the gradient index, this is another parameter which is important indicator of ongoing active deformation. So gradient stream gradient index is most commonly used to measure reverse slope. So it has been given as an expression SL is equal to delta H by delta L by into L. So if you take the longitudinal profile of any major or trunk stream which can help you in identifying the locations of active deformation, then you can have the length versus elevation. So the distance from the origin or any point from where you want to draw the longitudinal profiles. So distance in kilometer and elevation in meter. So if you have a profile like this, of course most of the profiles will look like this only, because you have the source area, headward area or headwater area, watershed, and then towards the mouth of the channel. And you want to measure the SL index at any given point. So what you will do is that you will take the center of that point, and you will have, so if you want to measure the SL index of this point, and so you will take the distance upstream and the downstream, and that will be the difference between the center of this location. So you have taken this stretch or the segment of the channel, and the center of this point will give you the SL index of this area. So from this, the difference between the height or the elevation, you will get the delta H, and the difference between the distance will give you the delta L. So center of the reach being studied, which will give you the this thing. So this portion will be your drainage divide, and this will give you the L. So from the drainage divide, that is the point from where you have started your the profile, from the center of this, the study which is being the reach which is being studied, center of that, and the distance up to the drainage divide will give you the L. So stream gradient index is sensitive to rock resistance, to erosion and uplift rate. So it increases with increase in uplift rate. So if you are having the area is continuously uplifting, then you will have a higher SL index of the region. So higher value of SL in rocks of relatively low resistance to erosion may be an indicator of recent vertical uplift. So you can do this exercise again either using topographic maps, or you can use the satellite data. So with the help of GIS and doing remote sensing, you can work out the SL index also, which is again a very important parameter to identify the ongoing local deformation or regional deformation also, because if you are having in regional deformation, then all rivers or the channels which are crossing the deformational area will show this will show the signatures of change in the SL index. As I was showing that in the previous slide, the change in the channel pattern, all the channels which were crossing the uplifted or the deformed area along the thrust fault in Himalayas were showing different type of channel pattern. Now this is an example from US which shows three fault lines, but this all three fault lines belongs to the San Andreas fault system. So San Andreas fault system, then you have a smaller fault splay in San Gabriel fault zone, and then Sierra Madre fault zone. So and this area is close to San Fernando city. So what it shows, that high indices of SL. So the blue lines, the white lines are all your fault, and the blue lines which are been shown here are the channels which are crossing the faults. Okay. So of course this this is just a sketch which shows, but not with the detail of the sinusity and all that, but what they picked up to show that wherever they are crossing, the SL index was different, and the reason was, we will see in coming bullets actually. So high indices of SL were found along the southern. So this is the north which has been shown here. This side is north and the southern side is this one. So southern and the eastern. So east is this part, eastern margin of San Gabriel mountain. So the higher indices were been seen in this portion. Both are the active faults. So these two faults are been categorized as an active faulting area. So high indices were observed along Sierra Madre reverse fault. So this one. So high indices were observed here, which corresponds to 1971 San Fernando earthquake. So even the deformation resulted because of the earthquake, because whatever we are talking about until now about tectonic geomorphology and all that, whenever there is we talk about the ongoing deformation, definitely the strain is developing within the rocks, and the strain will be suddenly released, which will result into the ground shaking, and that is your earthquake. So this also shows that 1971 San Fernando earthquake was responsible for deformation here, and that resulted into having the higher indices in the area, the southeastern area of the San Fernando region. And whereas higher indices in this area was because of 1971 earthquake. Low indices were observed along the San Gabriel reverse fault. So along this one, the low indices were been observed, whereas here higher indices were found because of the 1971 earthquake. However, though the San Andreas is active, low indices were observed. So even the San Andreas fault is one of the most active fault in the world actually. So even then, the comparatively, or you can say relatively, low indices were been observed on this two fault, because this was the higher indices were related or were correlated with the 1971 earthquake. So further, what it says that this all system, the fault system is in strike slip fault system, usually characterized by narrow valleys with crust rocks which can be easily eroded in the valley, which results into low stream gradient index. So one has to be careful again, because you have to be you need to understand that what type of faulting is also we are looking at actually. So this is a strike slip fault system. San Andreas fault system is a right lateral strike slip fault system, usually characterized by narrow valleys. So this portion is moving in this direction, this portion is moving in this direction along the fault, and so on and so on. So that will result into the crushing of the rocks, and which are narrow valleys which can be eroded very fast, and this can result into low stream gradient index. So this was the part of the gradient index here, and the higher one was been found over here. So valley floor and valley width ratio, again another important parameter which one can use high resolution topographic maps or high resolution satellite data, and one can easily identify the areas under active deformation. And this is again important because in most of the areas if we are going ahead with the construction and all that, we need to understand that which area is under the influence of the active deformation. So this is a simple cross section. So previous slide we were talking about the longitudinal profile, where we consider the elevation and the distance between the source and the mouth, whereas here we are just putting the cross section of the channel. So this is the valley floor here, and these are the two banks. So you have the right bank and you have the left bank. So what you take the parameter here, that is the width of the channel, then the elevation of the right bank and the elevation of the left bank with respect to the depth. So you will get an elevation here of the channel floor, and you will get the elevation of with respect to that of your east river bank and right and left river bank. So it is the expression or the equation which you can use to calculate this is VF. VF is valley floor ratio is equal to the 2 VF W valley width by ELD. ELD is this one, the left bank, minus ESC is the elevation of the channel bed, plus ERD is the right bank minus ESC. So valley incision is another important aspect which can be used to define the relative uplift. So relative uplift will result into the change in the channel profile, or you can say basically the change in the gradient or channel floor elevation. So change in the gradient will definitely affect the incision, and it will result into the formation of different landforms also. So cross valley profile can be constructed from topo maps or high resolution satellite data. Valley width can be measured from the distance between the channel, river channel marked by narrow deep valleys crossing the mountain fronts, and mountain fronts are associated to some extent, most of the time they are associated with the faulted ranges. So shows low VF value less than 1, large VF value greater than 1 are associated with broad valleys. Now this, if we consider this values, so what we should see is that most of the places where the river is crossing the active mountain front or seismically or tectonically active mountain fronts, then they will have narrow valleys and the values will be close to or less than 1. But if the VF value is greater than 1, then it will be marked by broader valleys. Now this exercise we did where along the Bias River, and the data which we extracted was from the satellite topographic radar mission data, SRTM data, where we got the DM and based on the digital elevation model we extracted this information. So what we have here is the cross section of different channel, and what we did was that we took the cross section of channel where the river was crossing main fault system. So this MBT in Himalaya is main boundary thrust, and this is the local, or we can say the branching out fault of MBT Barsar thrust. Then we have Palampur thrust, then we have Soan thrust, and then we have Jwalamukhi thrust. So what you find here is that most of the channels which are crossing this fault system are showing V-shape valleys. So if you see this one here, V-shape, you see along Palampur thrust, so along across river flowing across MBT shows V-shape valley, river flowing across Palampur thrust show V-shape valley, river flowing across Jwalamukhi thrust shows V-shape valley. However, river flowing through across the Barsar thrust shows broader valley, and this is also comparatively broader Soan thrust. Okay. So what we see now, because we have this right bank, left bank, we have the elevation of the channel floor, and we have the width of the channel floor. So all this information you can extract, and what you find here is, you carefully look at that VF value is 0.45. VF value here, Palampur thrust, is 0.32, whereas the VF value here is 1.54. Now relatively wider than this two, relatively wider, whereas if you move here, quite wide. And what VF value you are getting? 11.49, and this here, so VF value here is 1.7, again wide. So this exercise clearly indicate that this two fault system, and even this one, but this two compared to the rest is quite active, whereas this is also relatively active than this two, but this two are not so active, and this is quite showing very less activity because of higher VF values. So one can do this exercise along with the mountain front sinuosity and faceting, triangular facets, percentage of triangular facets, and also do the exercise with SL. So what we will do is, we will try, if time permits, I am not promising right now, but if time permits, then we will try to design one exercise, and you will perform the lab experiment on this actually. So we'll try our best. Let's move ahead and see what we found here is. So this is the table which shows the details of morphometric parameter used for calculating valley width, valley height ratio, VF. So as I was talking about, that we have ELD, ERD, so right and left bank, and then we have the Bias river. This is then meters, so elevation, then the base of the channel, and then we have the based on the equation what you used, you can have the parameter, and then we have the VF, that is the width of the channel here, and these are all the fault names which are been given here, and the values which we got was this one here. So even some places the value was almost 20, so this area is inactive. Okay. So it has been suggested that VF values with low V-shaped valleys, with low VF values less than 1 develops in response of active uplift. Broader U-shaped valleys with high VF values greater than 1 indicates major lateral erosion, because you have given enough time to the channel to migrate within the active valley. So that will erode sideways and result into the formation of wider valleys, or you can say U-shaped valleys, due to the stability of the base level. or to tectonic quiescence. So no tectonic activity is taking place, the area has remained quiet for long period, and there is instability in the base level. Whereas here the uplift, the active uplift will not allow the base level to remain stable. So the base level in this region is changing continuously, and the river floor is getting rejuvenated again and again, resulting into erosion and formation or development of V-shaped valley, which gives the Vf value which range is less than 1, whereas here the stable base value level results into major lateral erosion, resulting into formation of wider and U-shaped valleys, and the values of Vf will be greater than 1. Now these are few examples again which we have already discussed, so I would like that you go through it, and which can help you in identifying the local the responses of the uplift and the subsidence. So what will happen if you change if you are having an uplift and you are having a subsidence along the journey of the channel, which will result into the profile of deformation. For example, you are having an uplift here, then so you are reducing the base of the channel or the stream gradient here, you are increasing the stream gradient here, whereas with the faulting what you are doing is you are increasing the fall gradient here. So subsidence, this block has moved down, so this will increase the fall the channel gradient, whereas here the upstream is lowered and this is up, this is increased. So common channel pattern adjustment, if you have, then what you see here is that it will change from meandering to braided, and then meandering, then so braided to braided and meandering. So change, and this is the uplift and downfall thing here, and this is the area of warp which has been shown here. So this will result into the change in the channel pattern. And similarly, if you are having straight channel, then the sinuosity increases, and then the sinuosity decreases as you move from in the downstream side. So this is the up area and this is down area. So if you remember this, what we were looking at in Himalayas, where we are having the thrust fault. So this portion is the wall is up and this is down here, so that also will result into the change in the channel pattern. And similarly over here, so these are few examples which shows with respect to the change in the elevation along the channel journey of the drainage. And just a last example, that if you are having a regional tilting, then you will have the shifting of the channel, which is also commonly observed in most of the region because of the regional tilting or because of deformation. So this is the last slide. I'll stop here, and we will continue in the next lecture, talk about the two examples from Himalaya and Kutch. Thank you so much.